Welcome to day 2 of our WSA student show. Today we will be talking about representation and experiential and on computational design. We have a lovely speakers joining us today, Georgina Myers. She is part 2 architectural assistant and architectural computational MSc student at Bartók School of Architecture. She also graduated last year from our school, from Welsh School of Architecture, so yay. She was also chairing the exhibition last year, so very, very happy to welcome you back. She's currently preparing her research on machine learning in architecture for publication, working on Involve magazine. Her passions lie in digital design, of course, and responsive architecture, and using computational and parametric tools, as well as scripting and artificial intelligence to investigate and create architecture that addresses social and environmental issues. Welcome, Georgina, and over to you.
Thanks so much, Justina. I think that's a pretty thorough introduction. Oh, I should be sharing my other screen. Sorry, that's not helpful. Yeah, okay, great. So I hosted and run the festival last year, and as part of that, there was a day on computational design where I kind of gave a little introduction, because I'm really passionate about trying to help more people understand and be able to utilize computational design tools in architecture, because despite there being so many advancements recently and so many amazing uses for them, I feel they're still massively kind of undervalued by most of the architecture community, and even those who do know computational tools don't fully know the extent of what they're kind of capable of and what they're probably going to be capable of in the next few years. So in this talk, I'm kind of going to run you guys through my journey kind of into computation, why I'm interested in it, why I'm passionate about it, and how it's kind of changed the way that I think about design, data, and the realm of architecture, as well as taking you through some topics and applications of different algorithms and machine learning models, by example of some projects that I've done. I can't show any of my work projects, sadly, so these are all kind of academic works or pieces I've done for fun, researching wise, one of which is working towards making a grasshopper component, which I'm very excited about. So that was a great summary of what I've done by Justina at the beginning, but I am an architectural designer at Populous, and I'm doing my MSc in architectural computation at UCL. I mean, mostly day to day, I am still doing what I enjoy, which is working in Grasshopper and scripting. So I try to kind of find ways to automate and make architecture more interesting, exciting in what I do day to day. I also helped found and do the web design for Involve magazine, which also started at Cardiff about 4 years ago now. And I did my MArch and BSc at the Welsh School of Architecture too, and I graduated last year. So the first thing I kind of wanted to start with is how computational design is a form of architectural expression. I thought I would start this kind of talk with a little bit of honesty about how I got into computational design. I'm someone who's not always been able to draw, and therefore really struggled when I got thrown into architecture in my first year, until I kind of found the realm of 3D modeling, scripting, design, and computation. Then I really found I had the tools that I needed and wanted to be able to express myself architecturally. So this kind of started with basically starting in SketchUp, working my way up through Rhino, Grasshopper, visual scripting, and then kind of exploring all the other softwares that are out there. And now I've kind of delved into the realm of actual scripting in C# and Python, as well as looking into things like machine learning, specifically recently reinforcement learning, which I will explain a bit more about later. So in terms of how you approach a computational problem with the computational mindset, I thought I'd just cover this quickly, which is kind of what you do when you are approaching an architecture problem in general, I think. But it's especially important with scripting because to most people outside of it, or even myself when I was getting into it, it seems like a very large problem that you are not going to solve. It's just a wall of text, coding. So it's a bit terrifying, and I think it's hard to get over that initial hurdle. So the idea is you start by decomposing whatever problem it is, architectural problem, down to smaller parts, and looking for patterns within these parts or from other projects. You can bring in algorithms and systems that you've potentially used before. And it's focusing, abstracting away the kind of useless data and focusing on the core pieces of the project to be able to find step-by-step solutions or rules to follow or algorithms in order to create your design or do the optimization you're trying to do. One key thing I found helpful, and for me has been quite a large thing to get over, is the idea that all design on a computer is just data, whether it's stored in a list, a basic list, which I think we're all familiar with, or the idea in Grasshopper, which is the very confusing data tree for most people. Everything is stored within these two formats. And the idea of computational design is you're learning to manipulate and work with that data behind the scenes without having to modularly and manually model everything yourself. And once you start to understand the ways in which you can manipulate it as sets of data, as kind of clusters, rather than moving and drawing lots of lines manually, that's when the power really comes in, because then you're able to not only automate repetitive tasks, but you're able to see patterns more clearly and explore the data of the design in ways that you hadn't necessarily thought of before, because you're able to see it in a new light. Of course, there are different formats and approaches, and I think this is often comes down to whatever software that you're using. And I think it's kind of important for architects to explore what there is out there, not just stay within the confines of Revit, Rhino, and for some people SketchUp, because each of them allow a different methodology of form finding. So you're going to create a form that you wouldn't have necessarily otherwise have thought of. So for example, with Maya, you are manipulating points and lines and faces directly within the model. And I know Rhino now facilitates this, but it is a bit easier. And I think it's quite different in Maya, the kind of forms you end up with. I mean, hence why Zaha's work and the work from her practice is still so different. Then you have things like Houdini, which is mainly used for animation software and working with a lot of videographers. So what you can do is a lot of really large scale particle simulations, actually. And something that I did with this was actually doing a large scale rainfall simulation over the Brecon Beacons as part of my project, which I wouldn't have been able to do on any other software because it wouldn't be able to handle the amount of data it was dealing with. Then there's what we're most familiar with, those of us who do computational design, which is Grasshopper. I think just because of the things that it enables you to do and the amount of kind of open source plugins there are to help you get where you need to go. And also the kind of the customization that it also allows you to have. Revit, of course, which I'm sure most computational designers, I don't know how fond everyone is of it, but it has its purpose and it's very good for automation. But I personally prefer the kind of more exciting side to me, which is the creation side, where we get to explore different materials, and Revit kind of limits you in that way. But that said, with things like Dynamo, it's very easy to automate a lot of the work. So some of you have just graduated and you're going into your part 1, part 2 jobs, and a lot of what you're going to have to do is repetitive work. And I recommend you have a look into Dynamo as soon as you can, because suddenly placing 200 coordinate tags on a sheet or a drawing, it will be very quick work for you. I'll just briefly skim over this because I'm taking too long. Rhino, which we're all familiar with, great sub-D modeling, and 3ds Max, which again is very good for animations. And I know Wasim Jabi at WSA made some people look at Max scripting in my year, which is actually what got me into visual coding. I'm not sure if you guys are still taught that, but it is a very interesting software. But I would say if you do want to look into a scripting language, I would recommend Python or C#, but probably Python. These are kind of the simplest and most versatile languages you can use. So as I kind of mentioned, I kind of like to break the different areas of computation down in my head. They can also kind of reflect the different stages of creating a project. The first is kind of creation, so coming up with the idea or the methodology to create a form. This can be, you know, a machine learning model that creates a 3D model or an image from scratch based on what you tell it, or it could be you figuring out a really interesting algorithm that generates the design that you couldn't necessarily have done by hand. The next stage is kind of the optimization. So this could be structural, environmental. In this example, it's on a curved crease folding project. So it's kind of showing where the highest areas of tension are on the form. And things like this would allow you to, as most of you probably know, design very large scale buildings and see the stresses and strains that you wouldn't necessarily be able to see until you built it. The next, like I mentioned previously, is automation, which is not as exciting perhaps as creation or optimization, but it serves a purpose, which is it allows us designers to spend more time doing the exciting parts that we enjoy and less time, you know, annotating drawings. And I think there is a long way to go in developing how we automate our design process. There's a lot to be refined, and there is a long way to go, despite how I will show you later how far along we are in terms of generating images and spaces and even 3D models now based on word input. And the last stage is, of course, fabrication. This is an example that I found online, actually, from a research paper that I looked into on 3D sand printing. And there's obviously so many different methods of fabrication that it kind of overlaps with all of the previous 3 themes. And I think that's kind of the beauty of the computational process, is that each of these kind of sectors overlap with each other in different parts of the process. Like you could have an automated robot laying bricks for you, or it could be, for example, in 3D sand printing, you scan the bed of sand as you lay it down. So you're optimizing it as you fabricate. And it's the way in which these 4 different segments interact that really creates a really successful computational design process. So now I am going to take you through some of the projects I've done, as well as some of the methods and algorithms. And I thought I would start with something that might be a little bit more familiar and a little bit more traditional, because these are the ones I've done as part of my master's degree at Cardiff, where I was looking into rewilding the Brecon Beacons, essentially. And I did a lot of large scale modeling of rainfall to be able to make this work. So on the right, this is a math simulation Houdini, which I mentioned earlier. The different colors show the different speeds at which the water is flowing. And you can kind of get to see where the water accumulates. And I also then went further and simulated permeability of the soil by using magnets. So although there isn't necessarily a straightforward solution to what you're trying to do computationally, there will often be a way to simulate what you want, because that is all computational design is really, is simulating what's happening in real life. And then on the left, we have a similar kind of experiment done in Grasshopper. And then this is just another image of this project. Again, my workflow tends to be entirely Grasshopper based, just for the sake of being able to manipulate and work with the data as you go. So, you know, you've built your building, but you want it to be longer and the curve to kind of flow in the same way, or you want to maybe subdivide the buildings more and have more kind of pods going along the stretch. That's something that you could then change at the end of the design process, which is why I kind of really advocate for that, because it allows you to really design a system rather than designing a project. And I think that's really important in computation, especially if you are designing a lot of scripts, is that you are designing things that can be reused and adapted to work on different projects, not just as a one-off. And that again was going to be a close-up of the simulation, but that doesn't play. That's okay. Next, I wanted to kind of delve a little bit further into the realm of machine learning and artificial intelligence using a project that I did a year ago, well, a year and a half ago now, to kind of highlight how quickly the research has moved since then, because I do think it's quite astonishing. And I will give you guys some kind of resource where you can actually try for yourself to generate different image outputs based on prompts, because all these models exist on the internet now. But at the time, I trained my own machine learning model to generate images of space and facades based on descriptive inputs about how the space felt. The idea of this was to kind of investigate the creative process and how could an architectural creative process be carried out artificially. It's not only the model that is generating these outputs, but another important consideration is how it actually merges and integrates itself into our own design process as architects, because the kind of scary reality is that this is the future of design, right? Artificial intelligence and machine learning are going to be generating, automating, optimizing. I mean, they already are optimizing large parts of our design process for them. So how do we learn to work with these tools and kind of share our authorship of our work? So I quite like this quote by Margaret Bowden, who is a brilliant researcher in terms of artificial intelligence, and I really recommend reading about her works if you're interested, which is: artificial intelligence is the study of how to make computers do what real minds can. And some of the books I read were kind of done in the early 2000s, and they were stating, you know, computers will never be able to be creative or do what human minds can do. And now, you know, 20 years later, we're already admitting that we are not, you know, far away from the process being mostly automated in a couple of decades kind of thing. But for now, the creative process is something that we see as very uniquely human. So there's multiple steps to it, which is the preparation. So the research you do, the precedents you find, the images you get inspired by, the incubation. So this is the part that happens in the subconscious you're not really aware about, which is a period of time where you're kind of busy doing other things and there's ideas germinating in your brain. And then there's a moment of insight where the idea comes back to the conscious mind, and you have to put in the hard work to verify that it is a successful idea. Because to be a successful creative idea, it has to be valuable, new, and surprising, which is quite hard for machine learning. Well, it was quite hard for machine learning to get right, because oftentimes it was able to be new and surprising, but the problem was when we tried to make it valuable, especially to something as specific as architecture. So the model that I used at the time was very cutting edge, and it was called Attention GAN. And I won't go too much into explaining it, but the idea is you feed in, so there's a training stage that happens first, where you feed in pairs of images and these word values here, and it basically maps them through to be able to adjust and train a set of weights, because that is what's valuable in a model, is actually the weights, and that's what the training process is trying to do. So as the network goes forward, it produces the images, and as it goes backwards, it kind of checks on itself and updates its weights and tests whether or not it's doing the right thing. I chose this model because I thought it was particularly interesting the way that it mimics the human design process, in that a general adversarial network is kind of, you know, what describes, it's kind of a designer designing things and a critic criticizing them, and they're going back and forth, one improving the other, which seemed like a pretty good way of doing things. And these models are all trained on quite a small data set, actually. Usually they are trained on one that's about 300,000 images, which is actually considerably small. I did it on a much smaller data set than that, which is one that I scraped by hand from ArchDaily. Now, if you want to do this project, there's numerous researchers who are collating larger scale databases, so you shouldn't have to do that now. But the idea is that you're able to generate these outputs based on words. The problem is that at the time, the words didn't work as I intended them to, which is labeling each of them manually with 7 descriptive words, going through an Excel sheet, labeling hundreds of images. That did not work. So I used basically a concept called clustering, where there are basically 7 groups. And within, well, there's 7 levels of groups essentially, and each image has 7 labels, each of them describing what group it belongs in at a certain level. And this is basically what is its label and describes what the image is. So for my final model, instead of literally typing in words, you'd feed it a Preston image and it would try and generate something similar. So for example, for this vector input of this quite old Edinburgh looking building, it generated this. And then the same thing below, and you kind of see it was getting an idea for how maybe rectilinear the windows at this bottom one were meant to be and how fluid it was here. And at the time, this was a really, really good output. And then I tried to kind of control it using something called interpolation, where we're swapping these 2 captions around one by one, working from global to local. So these 7 levels I described, the top one is the local variables, so things like the window sizes and, you know, is there a door there, is there a spire in the middle, all the way down to the global one, so what color is the image, you know, how big is the building. And this is kind of how the machine describes it. And without going too much into detail, it basically plots every single meaning in something called latent space, which I think we as designers can visualize quite well because we're working in 3D space all of the time. So you're basically plotting this point in a 3D, sorry, not a 3D actually, that's just a way to visualize it, in a very large multi-dimensional space that we're not really able to visualize, which is why it helps to say 3D. But wherever it's basically plotted in this latent space represents what the word means. So if it's close to another word, it has a similar meaning. Like the distance from man to woman would be the same distance as from king to queen, for example. This is an example of the outputs. At the time, it did really well on the outsides of buildings or facades because it found an object to kind of latch onto. And at the time, these are really successful outputs, and it hadn't really been done for architecture, and I was very excited about it. And at the time, you can kind of see why I was excited, because this is the kind of outputs that were being done with the model that I used. And then you can see slight improvements as these models evolved. And this table on the left is actually from Google, because they've recently come out with a brand new model. And this point system kind of rates how successful all of the different models are. So you can see here, the one that I use, which was considered really, really good at the time, compared to the ones that are available now, which I'll show you a picture of in a minute. The improvements are ridiculous. And the key difference between this section here, which is trained on COCO, and the bottom section, and COCO basically stands for Common Objects, which is a massive data set of 375,000 images of everyday common objects that is trained on the model. And these are labeled images that the model then trains on to be able to generate these kind of images. The difference was that these newer models that were not trained on COCO were, instead of using GANs like I did before, they use language-based models. So when I just mentioned the idea of plotting a word in 3D space, that is basically the backbone of how these models work. They work on the words rather than the images. So this is what I was referring to when I was saying it's kind of embarrassing how much better they've gotten in the span of a few years. So the prompt here is, you know, a living room with 2 white armchairs and a painting of the Colosseum. And it is a perfect image of exactly what you'd expect, 2 white armchairs in a room. It understands the 3D dimensionality of space and inside room. And it's just also not only the fact that it's trained on a language model that makes a difference, it's the fact that it's trained on 650 million images, I believe. So it's trained on basically a massive set of images scraped from all over the internet. And now there is a bit of a barrier to be able to train one of these models yourself, in that most people don't have or aren't able to afford to hire a VM for a couple months for $5,000 to train one of these models and to host all of those image data on there, which means that most people would not be able to train the kind of model that is being produced now. And I mean, this one is DALL-E. So this one actually came out a year ago, just after I finished my paper. And since then, they have become even better. The machines are coming for our jobs, to put it casually. So this is an image also output by the next generation of that same model called DALL-E. You can see it's quite a detailed prompt here, but it's a very photorealistic, very high quality image. So you can kind of see the implications this could have for industries such as architecture, especially for things like visualizations, because you can start with an initial image and then add changes to it. So asking it to add furniture or to add people. So visualizations can be done like that. And if, for say, you want to come up with a design concept quickly, you could, create a prompt or mess around with several prompts that have the kind of keywords of your project and see what it outputs, and use those for the beginning of your design process. We are not quite at the point where we have perfect 3D models of space, although I did actually see one yesterday, which no time to throw into this presentation, where there is a game developer who has basically developed a system where you can input words and it will do the lighting, the materials, place furniture, place decorations on the wall, all of this in a 3D space. Of course, not one model, but several different models patched together, basically reproducing the architectural design process that we all follow. And then this is the most recent model from Google, which is Imagen. So this is just an example of all the different things that it can create for you. And it can even imitate the style of a particular artist or the style of a particular rendering engine, which is pretty incredible. Say if you want to do a visualization or a rendering mimicking the style of Unreal Engine, say, which is kind of what I've shown here. So this is some that I've done online, and these are the prompts that I've used. And these were generated in about 10 seconds, I want to say. And the barrier actually that I mentioned before about training and creating such a model yourself, it's not really a barrier anymore if you just want to explore, because there's websites that have these pre-trained models that you can now use for free, essentially, and play around with these prompts yourself, which I think is very impressive. I actually used this for a precedent image of one of my projects recently, when I was missing the exact one that I needed. And at the top, I've kind of included the kind of process images that it creates along the way. This is a slightly lower model. So the ones that I showed you, which is the DALL-E and Imagen, aren't available yet online unless you want to build them and train them yourself. But of course, the outputs won't be as good, because what is valuable in machine learning and the models is the weights, the trained weights. Otherwise, you have to spend a lot of money and a lot of time training the weights yourself. Something I was going to suggest was, if you guys want to type some prompts into, I'm not sure if you can vote for a comment, but if you guys wanted to type in a prompt and then you vote for maybe one that you like, and I'll put it in the model and show you how fast it is to actually generate an image like this. So yeah, if you guys want to type something in now, and hopefully by the time I get to the end of the presentation, we'll have something and I can type it in and kind of show you how quick it is and how far along we are with this technology in the way that it might be able to aid our design process. But yeah, to summarize, I think it's inspiring, but it's also, I think, very scary for designers things coming. But I think the right, sorry, I'll just go back, the right kind of path or the right mindset is to think that you should try and understand these tools because they are moving so quickly. So the sooner you try to understand them as they become more and more complex, you'll kind of have the background to understand it along the way. I'm just going to dive into some other projects that I've done using maybe more traditional algorithms, and then I'll also, for some of them, suggest some plugins that you might be able to use to kind of explore these concepts by yourself. I've seen this one prompt, great. If you guys want to add your own. Yeah, I think I can probably do 2 or 3. And yeah, I'll share the website where I'm doing it, which is, as I said, it's not the newest model, but you can do some pretty incredible work on there. So in terms of algorithms that I wanted to discuss based on some projects that I've done, one of those is wave function collapse, which is a really interesting algorithm for which you can use a plugin called Monoceros on Grasshopper to kind of explore it yourself. And this should kind of give you the basics to understand it. So the idea is we start with a grid, and all we kind of know is the location, the starting point in the grid. So when we are moving around the current square that we are, there's only certain options that we have as to what type that next square can be. So for example, you see to move up, it's only 2 or 3. To go to the right, we can only do a 1, and to go to the left, we can only do 1. So there's basically a set of rules that decide based on the current cell, what those surrounding cells are allowed to be. So if you fill it up, this is what that grid looks like. And this is kind of how I described the rules for it, which might not be the clearest thing in this exact example, but you can kind of see that 1 can only be attached to another square from its top half, and it can only attach to the bottom of another piece. Whereas 3 can only attach to the bottom of 4, but it can attach to the left with 2, and to the right also with 2. So you can kind of see these rules appearing. And these rules then decide how we fill a larger 2D space or a larger 3D space. And the idea is it's actually inspired by quantum mechanics, and it's derived from something called the constraint satisfaction problem, but it is a bit of a kind of trying to make it more complex than it is, because it really is a really simple algorithm. It just tries to fill a grid of empty spaces based on a set of rules. And basically, when there's more than one option as to what the next square is, it picks one randomly. And then it kind of carries on. So there's kind of different things you have to consider, which is the maximum and minimum bounds of the world that you're filling. What are the different components? So for example, here we've got 5 different color blocks, and then we've got the rules of connection of how these can connect. And basically this allows us, for example, in architecture, to iterate through different design options really quickly. It's just a fun thing I did, inspired by a project that I saw online actually. But the idea is it allows you to kind of play with different window openings really quickly, because by these set of rules as to what pipe can attach the next one from which direction, it's able to output lots of different shapes that are all, as you can see, they all kind of connect and work well and create a structure. And then this is the kind of longer project I did, looking at kind of MC Escher's work and how different architectural components are deconstructed and how they could be fit back together. So this is a really complex looking thing using the Monoceros plugin that I mentioned. So these yellow strings describe the rules of where we're allowed to connect to another block, and the pink ones are basically where we're not allowed to connect. So kind of things that are moves that are banned. And over here, I think these are roof or floor components. Sorry, it's not very pretty. But yeah, if you do use Monoceros, you can basically preview them and see all the different modules and the connectors. So in 3D space, obviously there's 6 connectors because there's 6 sides to a cube, which is positive X, negative X, positive Y, you know the rest. And then this is kind of an example of the output based on those architectural components here on the next slide. And the idea is, the staircases normally will lead to somewhere. They're not kind of, well, by lead to somewhere, I don't mean coming down another staircase is banned, because that's allowed. But there are certain situations where like there would be 2 in a row, and for example, that wouldn't work because the staircase doesn't really lead anywhere. And the idea with this is it kind of lines up with these exits and entrances we have, and this kind of color scheme and the playfulness of it was actually inspired by the Squid Games TV show, which was also apparently inspired by MC Esch's work. But yeah, this is a really good way to iterate through different designs really quickly. And I think it's quite fun to explore. I think it is also a free plugin. There is a pro version, but there is a basic one for free that you can download, have a play around with. There's also a really good website. I think it's Jam Pernaki, who designed it, and is a great kind of tutorial. It's very well documented if you really want to have a look through it. This is a project that I've done recently where I am kind of looking at an aspect of machine learning and doing it from scratch, which is kind of the challenging part. Because if you do want to do machine learning, there's a lot of libraries out there which allow you to skip all the complex parts of how it actually works with forward propagation and backward propagation. But my idea was to kind of do everything from scratch, get into the nitty gritty of it. And reinforcement learning is actually kind of the third branch of machine learning. So you've got supervised learning, which was the project that I showed you before, unsupervised learning, and then this one, which is reinforcement learning. And the idea with this project is it's called learning architecture, because the idea is it's trying to learn how to build buildings. You have to build on top of another block kind of thing. You have to build structures that kind of make sense, and kind of collating this list of rules that it doesn't have to follow. It's not an algorithm in that sense. It kind of learns as it goes, because the idea is behind reinforcement learning is that you give it positive or negative reinforcement. So if it breaks one of the rules that you've set, you give it, negative 10 points. But for example, if it decides to build on top of this previous block and go upwards, you give it a positive point because it's building a reliable structure. So to go a little bit into more detail about how it works, the idea is you kind of have 3 very simple components. You have the agent, which is this little dot that's moving through space, either putting down a block or doing a move, which takes an action. So like I said, putting down a block or taking a move by moving in space. It can rotate, so there's several different actions that it can do. And it chooses its action based on an observation of the environment around it. And this is kind of a cyclic process. So as it checks the environment, it does its next action and so on. And then it gets a reward based on what it's done, which it kind of stores in its list of how well it's doing at any particular state. So it keeps track of where it's been rewarded and where it's been punished. So it kind of knows what the best next step will be for it to get the most number of points. So to be a bit more detailed on what it can do, so it can either put down a block, move forwards, backwards, up, down, positive rotation, negative rotation. And it basically decides what the next move is on something called a Q table, which is what I mentioned, it keeping track of every single move it's taken and whether it's gone well or badly. And this is one of the simplest kinds, well, it is the simplest kind of reinforcement learning that you can do, because it doesn't actually have like a machine learning model. There's no back propagation or anything too complicated going on behind it. And if anyone plays games or is a gamer, there's lots of reinforcement learning models that have been trained to basically play video games. Ooh, I'm running short on time, so I'll be faster, sorry. So to be quick, I mentioned that there's kind of the observation step. So we look left, right, up and down. Is there something already here or not, and where we are? And that information feeds into the action space, whether we move, we build, or we rotate. And that results in a change of state, which we store in our Q table. So this is basically an average for every observation, so wherever we are, and every possible action we could take, what's the reward? And based on that, it improves these values over and over again to get basically really good at what it's doing. And this is a component that I'm developing. So it does actually work. I was going to do a quick demo, but I don't know if there's time. But the idea is you can kind of say how dense you want the structures to be, how large the area you want it to be, and how tall. And it's not always going to hit that because it's an algorithm. Because it's not an algorithm, it's trying to learn and do its best based on a set of rules. So there's always an element of randomness in there. But these are some examples of some of the outputs I did based on different bounds, different densities, and different height goals. And you can see for the most part, it builds quite logical structures that always kind of come back to down to ground level. And the ones, for example, where you've got a larger bound, it tends to run a bit crazy if you don't give it enough blocks. But it does kind of create some quite interesting structures. Definitely needs some refinement, kind of optimization, and more drivers behind what the user wants. But I do think it's quite an interesting kind of exploration into how we can get a machine to be creative without necessarily using unsupervised or supervised learning, which is kind of the current be all end all of intelligent design, right? The last project I was going to mention, I'll just do the demo quickly while it's open. But basically the idea is you just kind of click this and it will iterate through different designs for you based on, these are some pre-trained models that I've done. So you still have to train it, like I mentioned earlier, with larger machine learning models. And this is the kind of Q table that I mentioned as well, outputting here. But as you can see, you can kind of decide how much you want it trained. So the number of time steps, how many blocks you want to place, how dense should these blocks be, what area they should cover, and what height they should be. And then with the final one, again, you can kind of refine the number of blocks it's allowed to place. It gets a little bit fussier when I put more, because it takes a bit longer. But yeah, it's quite interesting. It's going through some refinement at the moment still. Let me just whiz through this last thing before I'm out of time. And then, okay. That's a nuisance, sorry. There we go. Okay, so the last project I was just going to show you was another kind of approach, again, working in Grasshopper, doing some custom coding to create something called curve crease folding. So the kind of things I've covered tend to be more machine learning, algorithm based, whereas this is kind of more mathematically focused and is kind of a different area, I think, of computational design, which is looking at how we deal with actual geometries like meshes and surfaces and how we can develop them further. And one of the big challenges with this is actually creating a developable surface. So the thing that was driving this project was creating a minimum surface structure, which you can do really easily using Maya, and is the same kind of form that you make with a soap bubble. So it's the smallest possible surface area, essentially. And how we could then turn this into a developable, so buildable structure, and then apply this concept of curve crease folding to it. So curve crease folding is kind of based on, and it's come from origami, of course, but it's actually got the potential to strengthen materials because it causes tension in whatever you're folding. So yeah, this is the kind of process I was describing. So you design an initial geometry component and then you turn it into developable and foldable geometry. So this kind of, again, I think the products I've shown iterate the kind of importance of designing a computational system or algorithm, right? Rather than something that is a specific code for a specific project. This is something that you could use again and again on different pieces and different projects, which I found particularly valuable in my work now. Sadly, I can't show you any of them, but that's kind of what I try to focus on. I try to focus on designing systems that I can teach other people to use and that we can bring forward into other projects so that we can build on previous computational work that we've done rather than having to do things from scratch for different projects. So as I mentioned, you kind of start with these minimal surfaces turn them into architecture components, and then design them into spaces. And these can be broken down all the way into a basic unit that you iterate and kind of rotate to form a minimal surface. This is done in Maya, as I mentioned, because you can kind of work with these very sharp edged pieces and then turn them into fluid surfaces. Just some more examples there. Again, kind of the idea of optimizing forms, geometries, structures, to make them work as part of your design process. So integrating all those different steps of creation, automation, and fabrication, and goodness, what was that last one? Basically integrating all the different parts of computation into your process and not kind of skipping out different pieces along the way. And then again, this is just an example of optimizing the mesh to basically make it developable or buildable. And that's one last picture. Yes. So yeah, iterating again, the idea of designing systems rather than projects. And although you are in your degree, so you are focusing on particular projects, basically a whole year at a time. If you focus on seeing if you can design these systems and help that drive your project, you're going to find that to be immensely valuable in not only the year that you're in now, but the years to come, because these are systems and tools that you can use over and over again. You can showcase them to companies, and then you're going to basically develop your own library of tools, systems, and softwares. And I think that kind of in itself is the foundation of doing good computational design. It's learning to design systems and learning to deploy them. And yes, does anyone have any questions before I dive into the quick AI prompts?
I think there is in the chat a few ideas for the prompts, and
okay.
I think people would like to see that first.
Yeah, okay.
That's actually fascinating, how easy, in theory, of course, it's looking very easy, and how much actually computation goes behind it and knowledge. So yeah, it would be great to see some examples.
I'm going to start with that first one. So it does take a couple of minutes to produce it. So I've just put that in now. This is a website called Starry AI. They give you 5 credits every day, and you can generate whatever you want. You can pick the style, as well as the model, and you can explore other people's creations in here to see what they've created. Oh, that's great. As soon as I show something. Has anyone got any questions while this is running?
If anyone have any questions, just pop them over to Q&A function. I use that one before that, because we will probably wait maybe until someone gonna come up. Oh, sorry. Mentella?
Yes, hi there.
Hi.
Thank you for this amazing presentation. I really enjoyed it. It was great. And since you're an WSA alumni, so any tips and tricks for the undergrads? You talked a lot about the exploring, and that it's not that hard to start exploring. And you said that you had a motive to start maybe because you weren't really confident with the drawing. I have the same thing. But do you have any ideas about more advices for the undergrad, especially, on how they can
kind of
start?
where to start?
Yes, where to start exactly.
I mean, I assume
or where
you're like
did you start
familiar with like 3D modeling in general.
Yeah. So
okay.
In 3D modeling, how can they start? Because usually, especially for year one, I was supporting in year one atelier. It's a problem always with year one that you have an idea, but it's really hard to present it. So if you have any software advices, tips and tricks for year one, especially, where to start from?
I'm not sure what you mean by an idea exactly. If you mean more like the concept stage of design.
The concept stage.
Because
exactly.
Yeah, I think that is a very tricky stage, and I think one way to approach that is potentially by kind of altering your method of designing, which is following the research like as much as possible to drive the concept. And I know this is the kind of thing that everyone says to do, but if you kind of pick it's like writing a good essay, right? So you kind of formulate a good thesis, a good question, and that leads you down a good investigation. Like that piece that I did for my master's on rewilding. I started by looking at flooding in Cardiff, and then I ended up rewilding in the Brecon Beacons, because that's just where the research took me, which is a bit ridiculous. It's not a real life project at all. And I found myself doing what was essentially a bit more of a landscaping project, which actually took me into what I'm doing now a little bit, is I worked as a landscape designer for 3 months before going back to architecture, because I think it's kind of interesting to explore all these different things. But I would say, yeah, to kind of let research and the logic of whatever your question is that you're investigating drive whatever you're researching. Don't rush the concept. Don't be afraid to kind of just let the research guide you and like dive really deep into that, and the concept will come, right? Because that's the whole point of creativity and coming up with an idea, is the more research you do, the more things you look at, the more kind of data or information you'll have to come up with your own new idea.
Thank you. We're having more questions.
Sorry, I don't know if that answered your question. We just made it worse. But if it was also about getting started in like computational software, I don't know if it was about that too, then I kind of would say there's 2 routes, right? There's visual scripting, which I think personally is an amazing route to go down. And then there's also the route of maybe exploring new softwares that your classmates aren't necessarily looking at, which again will give you different approaches to whatever design you're doing, right? Because they let you model things in different ways, which will lead to different concepts and different forms. Yes. And this is frozen. Oh, okay, it's actually doing something cool. That's good. Okay. Okay. Okay.
While we're still in process, there is a question from Patrick Barry. For the curved creases, is this something I could follow up with you after this? It was his thesis.
Yeah, sure. Should I put my email in the chat or something?
If you can maybe put your email like in the chat, or
yeah.
There you go. Perfect. Thank you. There is also another question in the chat, which would be, what would you say is the most essential software in the industry that students should learn?
It depends. I know you're going to hate this answer, but it depends what or where you end up working, because mostly companies value Revit, as sad as it is. They value Revit over Rhino or computational tools, because that is what gets packages out. And that is the work you will end up doing as a part 1. And probably a part 2 is making construction packages. And while it's not the most enlightening work, you do learn a lot. And there is a huge value of just having experience. I did my practice for 1.5 years. So I worked halfway into my last year, my master's as well, part-time. And I was working in Revit the whole time, stages 4 to 7, basically, so late stage. And companies in my part 2 found that really valuable, because I had so much Revit experience. And that is like the reason that they hired me. And then I kind of snaked my way out of the Revit pit into something where I was more interested in working by kind of networking within the company, which I think is also a really important thing to do. And I think it's especially hard with the pandemic and everyone working from home kind of thing. It's quite difficult to kind of talk to other people in the company and see what else is out there, because the chances are you will get put in quite a package-based role. But I would say the two most commonly used like softwares are Revit and Rhino. And again, if you are doing concept design and your company wants to use Revit, there is a program called Rhino inside. So you can basically design Rhino inside Revit. But that said, I would say those are the two key ones to learn. Beyond that, it's kind of like, if you know them, it's nice. Will there be an opportunity for you to use them? Maybe. I've been really lucky with where I've kind of been put in my own company. Like I said, through kind of networking and kind of being like, I'm really good at this, can I work on this project? Is that I've actually gotten to use some of my master's research already, which I've literally just finished, which I really wasn't expecting to actually be taken seriously and get to use it. And like I mentioned before, the value of designing systems rather than actual projects is I've designed some systems now for a particular project that I'm using, but it's kind of sparked the idea of building up an internal library kind of thing of different scripts for the company to use. So while Revit skills are the traditional route to go down, you can kind of show your value in other ways. But again, there are a select number of companies that will kind of recognize and appreciate that skill set. Unless what you enjoy is automating tasks in Dynamo, then you can, prove your worth to most companies, to be honest. But yeah, that's something I forgot actually. If you do know Revit and you know Dynamo is quite rare for people to know. So if you can show that you can automate tasks and save companies time, that will be very valuable as well.
Do you have any recommendations for people to further initial interest in computational design?
Yeah, I would say there's a lot of online communities that you can kind of join for inspiration. And I do understand that there is the feeling of, oh my God, everyone's doing all this amazing stuff and I can't do any of it yet. And I experience that too sometimes. So I completely understand the pressure, but it's worthwhile kind of seeing who's out there on platforms like Instagram, like Making a Design Instagram, because I've met lots of really interesting people through there, some of whom happen to do my master's, the same as me. Someone else, lives in the US and runs a podcast, is a really, really fun person. And yeah, there's different, I don't know, just by joining these communities, you can kind of ask people questions about their projects and kind of get inspired by other people's ideas. And I would say that Instagram is probably a good place for that. LinkedIn is a bit formal, so you don't get as many young designers on there, really. So I would say that's probably the best place. I know there's some Slack channels as well, but I'm not really part of those.
All right. Unfortunately, we ran out of time.
Yeah. So do you guys want this link to this website as well? So you can have a go.
That would be great. Yeah, definitely.
Put that in the chat.
Yes.
But yeah, that is a town built along an tidal energy embankment using slate and granite. That is your picture. Which I think is quite nice.
It looks really good, actually. Amazing. Oh yes. Perfect. Thank you.
Sorry. Also, very quickly, in terms of other resources, there is a website called Parametric House, which has lots of great tutorials. And honestly, there is a lot of YouTube tutorials for everything that you could want. There's some really great channels out there. Just look them up. And if you don't know where to get started, I got started with a Grasshopper textbook. So if you want to learn it, there is so many more ways out there to learn it now that are much easier. And sometimes it really helps though to have a project to be working on and driving towards. And there's also some free courses on LinkedIn Learning and Udemy. And yeah, there's so many.
For me, it's always the YouTube. It's the way to go for the first thing, and then you're dropping into, so you're always finding the links.
Exactly.
Thank you so much, Georgina. That was really great.
Thank you.
And we learned a lot, and it prompted actually a lot of questions. So it's really, really good. Thank you very much.
Thanks for having me.
So now we were going to move to a second speaker, which is Alexandros Kallegias. And Alexandros is a senior architect engineer that studied at the University of Patra and finished his MArch at Architecture Association School of Architecture in London. He has substantial design expertise, having worked for Zaha Hadid for a number of high-profile projects. He has worked also on a variety of projects throughout the Greece. He's a member of UK Transformation Northwest cohort, where he does the research on the use of data in AEC industry. He has taught on numbers of prestigious universities such as ours and AA and Bartlett, etc. His work has been presented and published in peer-reviewed papers and international journals. So welcome, thank you for being with us, and over to you.
Great, all right, thank you very much, Justina, for the introduction, for the kind introduction. I think I should share my screen, right? Yeah.
That would be a great idea.
That's a good idea. Let's see. I don't really know computers that well. It's just a fan. Hold on. Let me find the button. Here we go. This should come up now.
Yes, we can see everything.
Great. All right. That's good. Can you hear me all right?
Yes, perfectly.
All right. Cool. So I'll try to keep it on time so that we're also very relaxed and then we can have a conversation perhaps afterwards. In fact, it's very lovely to be here today. I also enjoyed the previous presentation, and it is actually, it's exciting to be invited to give a talk at the World School of Architecture, and specifically at the exhibition show, and then talk a little bit about my vision of architecture, such as it is. Now, when you have someone looking at the kind of things I do in architecture, they will quickly realize that a big part of my work is quite different from the traditional side of our profession. So what you see here are prototypical structures that have been made possible by incorporating computational tactics into the design and the production processes. And I would like to talk about these processes in the context of the times that we're living in, as we're currently inhabiting the information age. So I'll show you a clip from a movie called Minority Report now. The movie is all about the future technology that makes predictions about human behavior based on human data. So in this future scenario of our world, the main character is trying to escape the police. He's actually entering a shopping mall. And the thing I find very interesting here is the scene that he's being bombarded by clusters of information as he moves through the building. And you may have noticed those cameras are actually targeting his eyes. And that's a way that the movie is trying to demonstrate that these are very personalized commercials. You may have experienced that already. And then what is interesting is that this movie has been filmed, I think, 20 years ago. But I'm sure you have been, experienced your own sort of personalized advertisements on probably your phone or computer. But then another very interesting work that is it has a sort of critical look at the technological forces that are shaping and are drastically transforming the early 21st century, is the work of Michael Najjar. And I'm putting it here because I think it can start to generate a lot of discussions, or at least provoke some thinking about, how we could combine the realistic with the intangible elements, as this is what he's actually doing in one of his paintings here. Actually, it's a photograph. And what he did, he actually reshaped it digitally. He took all the contours of the mountains and made them follow the vicissitudes of the Hang Seng stock market index for Hong Kong. So basically, he's trying to make the visible, make visible what is normally invisible to the human eye. And that's the information about the stock market overlaid on a on a photograph of the mountainside of Hong Kong. Now, some more tangible examples that I've seen through the achievement of 3D printing technology. And here we see customization of the design, which allows for higher performative output to items such as a medical waste binder or shoes. These are items that so far have been produced in a factory line type of way. And then it's a must for this sort of industrial mass production line. And then we also have things like this, the useless box. Now, it seems useless, but this is, in a way, another critique towards current day technology. And in fact, this has been put together by a computer scientist, the one who actually co-founded the MIT AI laboratory. And I think this is, again, another critique towards the things that we can achieve with technology. And for our industry, I think it's important to ask ourselves, how is technology influencing architecture in our built environment? Now, if we consider a city, if we consider the urban setting, and we look at any city from above, it becomes clear that what we create as architects, such as a building, is in fact a system situated within the larger system of the city. And as soon as we can see that, we can then start to understand and study the changes in the qualities of space, the interaction over time, and therefore tease out the information that shows the evolution of a place or how the area evolves. Now, for instance, as soon as I overlay sort of a color map of the taxi route densities of London, this is the city of London, and I believe that each one of you has already got an idea. Even if, let's say, you've never been to London, you probably got an idea of what means to move in different parts of that city and what's denser, what's less dense. And it's all a matter of like representing information overlaid over an architectural drawing such as a city plan. Now, another useful way to study a city is through analogies, in my book at least. And this is a good example of what I mean, that comes from the visual thinking of Oswald Matthias Ungers. So Ungers creates cartographies and analogies of the city with other systems, such as the living system of the human body or the working system of a car. And I think it's in a very smart way, positioned one next to each other. And then we can already start to speculate about the different correlations among those systems. At the same time, I'd like to put another reference for your information here, is the work of Darcy Wentworth Thompson. I'm also very much intrigued by his work and the book that he wrote on growth and form. What I see here is what I use from this reference is his interpretation of the species found around nature, around our world. So he talks about having a grid, and you can overlay that regular grid over a species, such as the fish here. And as soon as you start to deform that regular grid, as soon as you start to move the points that are connected to each other, then that will generate all the different the other species of fish that you may find around the world. I think that's a powerful thought, because then you can start to decipher certain aspects about the things that exist in the world around us and how they come together and how they are formed. So in my line of work, I always enjoy going into the details about natural processes and try to decipher them, try to understand how things come together, how they operate. Not sure if you ever consider looking at different phenomena and start to draw different analogies, as I enjoy doing, like I said. And here, what I'm trying to tell you here is that there are phenomena in nature that have different scales, but the pattern formation actually can be linked together. And we can see pattern formations from microscopic scale of a cell to geographical scales or the scale of our own universe. So in that way, I think there is some sort of underlying sort of rule of formation for this phenomenon, and we can decipher them and use them in architecture. Let's carry on. So, being a little bit more architectural here, this is the example of the palace of a chief in Cameroon. And what we have is one of those cases where we can decipher the way that this has been put together. And it's in fact using a recursion method. You can see this actually in math. I know not everyone is excited about math, but in any case, I think visually it's very clear, it becomes very clear as you break down the elements of this palace, and you can identify repeating items in a self-similar way. So you have that square that is then scaled down, rotated, positioned, and that repeats again and again and again. And you end up having the palace itself. So this is a procedure, this is a sort of a technique that you can follow, and then eventually end up having even more elaborate patterns. And then there are many examples that are found in Islamic architecture. So this is also another level of complexity that we see around. But these are all following very basic rules of geometry. And so how can we use technology to boost such an approach? Well, I'm going to go back to the examples that I mentioned about being inspired by nature. And here, one way is looking at birds flocking or school of fish or termite nests. So these are a few examples that I can understand that this can be used for design. And the way this works is that they're not following a leader. These are actually flying in a self-organization way. So what they do follow is simple rules based on relationships, and these rules are embedded in their DNA. This natural phenomenon was mathematically solved by a person called Greg Reynolds in the 1980s. He wrote a paper in 1987 where he describes the three rules. These are separation. So those birds don't really come too close, they don't clash. Alignment, they have one direction. And cohesion, they still come close enough to become one body. So this actually can be used in vector math, which I'm sure everyone remembers from high school. Carrying on though, some examples. For instance, in computational architecture, similarly, you can define components, you can define forces, you can define relationships. And then with that, what you get is the overall form and the behavior of that form emerging from what we would call local rules. This is also known as a bottom-up design approach. So there is no design leader in a sense. There are like many different things that we want to achieve. And then we simulate that, we run the code, and the code is giving us different outputs as we could tweak the parameters. So how can we use this now as a design principle? And then how can we take into account, say, materials, fabrication, things that we find in architecture? A useful aspect of computational design is that you can draw many and different types of information from whatever it is that you're creating. And I'll show you now one example from a building that I worked during my time in the office with Zaha Hadid Architects. So this is an image of the outer skin of that building. It is in fact a diagram because it depicts information about the form itself. With the use of 3D grid, each point that you can see defines the trails and the curves of the building's envelope. So when you have that, then in turn, you actually enable a kind of coordination or other actions that involve coordination between the different parts of the building, such as the interior program or the internal structure. So regardless how sophisticated the form can be, as soon as you can be very specific and explicit about how it's being put together, as soon as you can calculate certain things, even from early on, then the next steps will actually be will be easier. Now, this is how the building looks like as it was designed. It's an opera house. It has an 1,800 seat theater and 7,000 person amphitheater. And it also has a performance space, an experimental performance space. So it's quite a building that has been designed for the King of Morocco. Now, the interesting bit about the form and what I showed you before is that you have an image such as this, but then you need to coordinate with other people. So how do you do that? You actually have to, create a series of different package drawings and manage to communicate the different information from, the say early stages all the way to construction. And this is actually coming from one of the consultants of this project. It's a firm called New Technique. They were involved with the making of the envelope, and now you can see a translation of those lines and then a population of the surfaces with different points that each one has actually a tag. It has an ID, and that can be traced back for the manufacturer, for the construction stage. So these follow a certain logic as well, and that's what's very important to remember as you go about maybe creating more irregular forms or the way that you do them. It's always good to have an underlying sort of system of how you can create them. And that's because there are different players coming into the making of an edifice. And then that's the nature of our profession. It's interdisciplinary, and that means that there are different consultants that are involved. However, the architect needs to be aware of the totality of the building. It's almost like the Renaissance architect that was everything, was doing the design, was doing the building, in that sense, during the information age that we have different disciplines offering specific data about the project. It's important that the architect can understand those different parts that are coming together and make sure that the sort of synthesis of that is leading up to the actual project delivery. And what you see here is an image that in fact shows all the different items that come together for this project, from the external facade, the interior facade, the plumbing, the mechanical engineering, the structure, and the architecture, of course. So this is not frozen in time in a sense, even though this is a screenshot. This is an iterative process that you go back and forth and you fix things. And eventually you do that in order to help yourself to get to the end of the project in the most smooth way possible. And that would include also simulating construction. So, in that sense, what you can do is you can actually put all the different parameters together for the building to be built. And in that sense, you can almost predict or at least anticipate anything that might not be in place at the right time, and then tweak that and be able to, avoid any major issues during construction. So, while this is happening, in fact, the building also is being constructed. This is an old photo, but I hope now you can start to see the correlations of the different stages, different ways. This is a very quick overview of that. That needs to come together in order for a building of such a scale to be completed properly, and that's including the sort of sophistication of the design and the coordination with all the different players. But I want to go back now to, the kind of applications at a more experimental side that we can have with computational design and architecture. So I'm going to show you a few examples through workshops that I have been running. And then some of the techniques that that have been used throughout these workshops that have been with students such as yourselves and then fellow tutors and researchers. So what I have here is, these are like two simulations. We talked about different ways that nature can be, motivating or inspiring the design process. At least in this case, what I'll show you here on the left is a number of different points that are acting as bots. So they have a certain behavior that is defined by rules on the side here. So these rules are pretty similar to the ones I described from the flocking phenomenon. So, you have cohesion, you have separation and alignment. So when I run this, what you notice is that they recognize the surface here. These are acting like as a grid as well. And they're trying to follow based on the rules that, we have defined here on the side. So they're trying to follow as best as possible the surface itself. So you see them like climbing up slowly, and in some cases they come together, and in some other cases they're branching out. And again, this is what we call a bottom-up approach. So there is no, magic hand that has designed something. It's more about design rules that we set up in a sort of computational model, and then we run simulations with it. Now, this is one stage. And the second stage is the video on the side. This is another simulation. This is the second stage where all those different trails that you noticed now have been transformed into a more volumetric form. And then they also have, so what you also notice is probably a layer of colors on it. So these are not, colors for the sake of colors. These are actually represent something. So they represent a specific kind of information that relates to the displacement of what this could be as a real structure. So trying to simulate that in the digital environment and understand where it needs to have stronger elements, where it needs to have reinforcement, and use that as another design principle to run again the code. So now we have a little, flock of voids going up the surface again. You probably notice them here. What they're doing, they are depositing a secondary layer of trails. And they are doing that by actually trying to understand where it may need to be, reinforced. So in a way, this is an iterative process that you go, again and again until you're happy with the result. Now, this is all very digital. What I will show you is also how you can combine the two, the digital and the analog side of design explorations. And you can do that, you can do that in many different ways. What I'm showing here is a sort of simulating circle packing. Circle packing is, there are different examples that go through here. But what is important to keep from this one is how you translate the digital side with the physical one, and maybe how one can inform the other. And it's not just like one way, but it also goes, both ways. So in this particular case, in a workshop in Athens, what happened was, together with the computational side for the design, there's also the computational side for the construction. And part of my interest is creating prototypes for interaction, for interactive architecture. So some of the things that you may recognize or may not, so this one on the side is something called a servo motor. So these are very easy to get in the market. These are like open source, they're based on an open source coding platform called Arduino. So you can start coding, because all of the things you see here are done with code. Not to be scared. we can talk about that bit, but the main issue is how you start to blur the lines between the digital and the physical, and then doing that through experimentation, right? And you can start off with like a small scale such as this, and then these are different things that you might be interested in having and using for your own design. So there are different stages. These again are a few snapshots from workshops that I've been running in the past. Again, this was with the School of Architecture in Athens in collaboration with the School of Architectural Association in London. We came together and we created a series of different creatures, let's just say, that can move, that can respond to external stimuli. And we did that by trying different things. And, we kind of had different teams coming together. So we had that sort of collaborative aspect that each one cohort had one particular task, but they all needed to communicate. So this is, again, another way that design and architecture can actually work best when it comes to having a team or having teamwork. And we were using different things such as, it was a combination of rigid structure using timber and more tensile structure using fabric. So, scaling a little bit more. This next example is one of the cases where it was an intense workshop of around 10 days. And the idea was to create a sort of a pathway, a passage, and that would have a certain features that would allow people to communicate through that. So different students came in for the workshop. What happened was I ran it in a way that there were tutorials so that everyone would be introduced into the sort of world of computation through code. And it's not as scary as it may sound. I don't know if you have any experience before. I think most of you are first year, so I would assume you're now discovering things. But at the same time, we wanted to translate that design into something real. So I'll take you through that with a little video here. I don't know if it's. Is it working fine or is it frozen?
It's like breaking up a bit.
Oh no, wait, there we go. So, oh, come on. So these are like a few of the proposals at the time. So it's getting frozen. These are proposals from the students that they came together, and then we ran a competition. And this is the winning one, let's just say. So we had different strings that were crossing the two sides of the path. These are very tensile, and they would open up as a person would go through. So that was the main idea. How to do that, how to make that move. And that would be done by having another system. So this is the scenario. You would then have two people. Let me go back a little bit. So this describes the scenario of interaction. You could have, the neutral state, no one goes through. There is one person going through. And I'll explain why it's called hostile state. And then there's the friendly mode and kinetic mode, different kinds of modes. So this has been the brief, that was put together with the students. And the next bit is the diagram that describes this. Sorry. And we can talk about the tools that we use to do that. It's not that important right now. But here it's a simulation of how the elements would move. So we would use triangulation, we would have different triangles with sort of the strings going through them. And in the middle of that, we would have other strings that then we would rotate in order to be pulling up and releasing to drop down those strings. So we would simulate that process. We would do that beforehand. And then we would map out the different panels the ones that are interactive and the ones that just have lighting. And this would be the sort of nervous system of the structure. And what you see here is the Arduino set that we use. So we have servo motors, the ones that rotate. We have these different sensors that pick up, let's say, what you have there as ultrasound. This sensor is something that picks up movement. So similarly to when you move by and some light open up or something, this is the same thing. So this would generate the kind of data to start to activate the system. And this is a kind of diagram of that. And now, you know, we all come together to build the prototype. So we have the timber framework, and then we start to put together the strings. I don't know why it's as so see, the middle one is rotating, and as it's rotating, is actually it's being pulled up, and it actually allows for the strings to open up. So it's, I don't know why it's doing that. Apologies for that. But this is quite important. I want to show you the experiential side of it. So while we were testing that, eventually what you got is to actually be able to go through it. So as you would go through it, this would normally be up, depending on your height also. But then if you stop, then the structure realizes that you have just stopped there and becomes hostile. So it closes down on you, you know? And in order for you to escape, someone has to go by. So you will see someone passing by. And in that sense, now the structure is opening up again. And, you know, you have that friendly mode where you have a person, like a friend, helping you out. So, you know, this is pretty much the concept from, you know, design fabrication using also computational techniques to simulate, to be able to understand what it takes to fabricate that and all the details that I just mentioned. Let me carry on with one more example here. This will be the last example that I'll show because I think I need to be on time. So this is another case of an interactive prototype that was the output of a workshop that I ran in 2016 in Hania. This is a place in Greece. It's an island, you know. Sorry, I'm thinking about summer. So it's a collaboration with the Architectural Association as well as the Hellenic Open University there. And what happened was we kind of see an opportunity to communicate different information of the city with the citizens or with the people there. And those snapshots are from an exhibition we did with this prototype. So like I was saying, we had different partners, but then people came from different parts of the world. And eventually the cocoon kind of structure is made out of fabric, completely out of fabric. And I'll take you through the process so you can see examples of computational design that you can also perhaps consider for your own, you know, interests. This was also during a 10-day period. This was quite intense as well. And we would run different tutorials with the team that I had there in order to bring everyone up to date. So people had no experience with computational tools. And the final output is something that came through that same process of putting together proposals and picking the one that we liked the most. And eventually this was also done, you know, exhibited in one of the exhibitions about technology in Berlin. And this is a screenshot of that. What is interesting is that the cocoon is accessible. And this is part of that, and I'll explain the process. But the interesting bit is that it was so good that people who went in sometimes didn't come out. And one of them was like a couple, you know, and this couple didn't want to go out. And it was a bit awkward because there were people around, and we were waiting for the next people to go in and experience that. So, that says something about the, the success of something that started off as a prototype. Now, to get you through the details of that, as I mentioned before, we have, every city, at least every major city is distinguished by its own unique built environment. And what you see here is that city that I mentioned where we were during this workshop. And this is one of the diagrams from the team describing different attributes of that city. And, what you can achieve is that through time, you can observe the city's transformation, and it almost resembles the growth of a species. And this is probably, linked to the things that I was saying before, because that you can actually correlate that with the sort of different personality of the species with the edifices that you have there, such as the arches. So one of the teams went around the city and then documented the different arches of that, and actually demonstrated the evolution of them as well. So there are different, attributes, whether it's in terms of cultural significance or technological achievements. I think the urban fabric of various locations can allow for that specialized and more genuine set of design qualities, because every place is different, and I think that has always been true, and then that has always been the most interesting bit for someone to go and visit a place, for example. And we were trying to tease out that information, and some of the times people here, they were trying to map out the coastline, they were trying to map out the city, the city line. So and then translating that in different ways, overlaying a kind of visual sort of way of communicating information with colors, with a gradient, and in other cases, understanding how the hours work with the sunshine, and then converting that into a graph, and I'll explain why. So this is like one of the ways that the clusters of information of the city can be pictured as they fluctuate, okay? But then how can we make use of that? Some of the cases with the teams were to sort of create those abstract models. This is coming from a team that looked at the skyline and start to move the different points of the skyline depending on different aspects of the city. I think they were looking at densities over there. And other times it was all about the different times of the day and how the form would change over time during a day. Some quite interesting approaches. The most successful ones are usually the ones that are very, straightforward. Now, another team went ahead and used an application. So they had an app that was able to map the different sounds of the city. So, like any sort of species, you have different sounds. So they wanted to map out what kind of sounds that city was making. And then you can probably see on the top right with colors, colored dots, the sort of the route that they took, and the different colors demonstrate the different densities of those sounds. Because eventually we want to convert that into something more tangible, visual, something that we can work with for architecture. And then they came up with different ideas. They came up with creating those sort of mapping images there for different times of the day. Now the next bit was, how do we go about creating the form? How can we start to start working on the form? So we went through a series of different trials with simulating inflation. So each team were going about doing their own little tests. They were trying to understand the implications of the forms they were making if those forms were to be inflated. Because that was the point. We wanted to create an inflatable enclosure so that it actually it's not random, but because of the design, it opens up in a specific way. And eventually the experiments led us to create our own kind of species of enclosures with different attributes. So with the use of, again, computational techniques, we're able to populate that surface with as many points or whatever we wanted to make them on it that would demonstrate different aspects of that, of the city, in fact. So that's fine. Now we need to actually come on, find a way to fabricate that. So the different teams started working with paper. You can start off with like basic stuff. You can start to consider how you can have that flat piece that you can then sort of start folding in order to create your enclosure. However, the paper wasn't good enough because it wasn't it wasn't very tensile. So then we started looking at the different fabrics that we could have, and eventually we would come up with different patterns on the fabric itself that would be following the designs that we simulated before with the inflations. So that's fine. We now have a strategy for fabrication. How can we start conveying information of the city, those unique elements of the city? How are we able to do that? So a couple of ideas came through, and what we eventually had was a series of different simulations with what is known as fluid dynamics that would then be projected onto the actual enclosure. So yet another team was actually in charge of creating these different simulations that would follow data such as the sounds that would come through, or they would follow the sort of like skyline or the coastline. So different densities would mean different things all the time. So this is a sort of a series of different projections that then would be placed onto the enclosure in order to communicate that aspect with people who would walk inside. And then, thanks to the computational side, we would facilitate the fabrication bit. So we would be able to rationalize the form, break it into parts, and then flatten it out so that we could then use very basic tools such as sewing machine to put it together. So coming to the finish, I think my time is up. I'll show you a video of the last moment where everyone is quite eager to see this working. So we have everything put together, and then we start to inflate it. So like any architecture project, this is the last day. We had to have something for the exhibition the next day. It's nighttime, as you probably can understand. We're very stressed. We didn't have time. We only had one chance to do this right. So we had the design done. We were happy because it was coming together. So you see everyone is pretty much excited. They're clapping and everything as the prototype gets inflated. So it is. You had to be there to understand. If I can give you an analogy, it would be, think about your finals and being happy to do that because you actually managed to do it. So that's the same feeling. The thing was, we didn't know if it would be so very good success, how successful it would be. So it kept on going. That's where someone got really, scared because we thought it would explode. And we didn't have another one. Thank God it didn't. Thank God it did not. We managed to, stop the whole thing in time. It was such a good way of fabricating this that we were able to actually make it work and fill it up with air as much as we wanted, and it would hold. This is from the exhibition there. A brief description about how it's put together. And what you see next is that sort of projection of the information, the visual information there on it. And as I was saying before, you could actually enter this. You could fit quite a few people inside. And when you would be inside, you would be, in fact, able to be immersed and forget about the world outside. This is how it looks. So, yeah, coming to an end, I guess, again, when someone sees things like this, they think this doesn't seem like your traditional thing that you would do in architecture. Yeah, that's probably true, but you can get to a real building, even though you might start thinking differently. And I think this is important, especially for people who start off now. And given the fact that we are in a different sort of age with all the different information coming through, I think we need to have a say as architects. We need to be, a little bit driving the whole thing and where it goes. And if that means revisiting the process of design and fabrication, I think it's worth it. I think, especially for those who start the journey of your education now, open up your minds, try to see as many things as you can, and maybe sometimes this would make sense, sometimes it may not. Some make sense more to others, but experiment. I would say open your minds and explore. I will hold it there now. I think my time is up, right?
Yes, it's actually 10:02, but it's fine. We run over anyway. So thank you very much for this inspirational talk. And this is time for the questions. So I see the raised hand by Ashley for like a half an hour already. So let her talk. Ashley?
No.
No? Ashley? Nothing?
Hello, I don't think any of the attendees can have their mic unmuted to talk. So if anyone has a question, could they please just write it out in the Q&A section or on the chat, please, if that's okay. Thank you.
All right. If there is no one yet to pose the question, maybe I could ask one. So you worked for Zaha Hadid and you mentioned a couple of projects of hers. As this exhibition is about process, how do they start the process? How everything worked there? How the process looked like from the beginning, going onwards? How the inspiration has started?
That's a good question, Christina, actually, because it's crucial how you begin. I think you were right to consider, the starting of something as very important. And the way that this would happen with the office, it would be by having different when it comes to the design, it would be by having different ideas on the table, literally on the table. And this is the times when Zaha was around. So different people of the office would, within the team, let's just say within a given team of a project, would put together ideas about the project given the brief. So we would know the brief, and then we would start to kind of propose within the office. So going through a process such as presenting now as a student, let's just say, it's crucial because you start to build up that knowledge of actually really making a case for yourself if you really want to kind of make it to the industrial side of architecture. So in that sense, we would have different proposals, and then one of them or two of them or some of them or a combination of them would come through, pretty close to what I was describing about the process with the workshops. Tool-wise, there would be, because the office is quite diverse in skills because of the people that it has. Even though there are some prevailing tools, a lot of proposals will come from different software. Maya is one. Rhino is another one. And the process itself would be the design bit, the sort of, sculpture thing would be a combination between Maya and Rhino. And then we would have rationalization with either Grasshopper or Dynamo. So I was in charge of doing that in some of the projects that would go forward from, let's say, the competition stage to the actual construction stage. So we would then have to rationalize the design, and then we would use things like, unfortunately, like it was mentioned before, Revit can be very difficult, especially with forms like the ones that Zaha's office is creating. It's getting better and better now, but it's still not very flexible. So there will always be a combination of software, and there will always be a sort of a process, iterative process of going back and forth. So yeah, but the early stages would be a very long process of a lot of different ideas thrown on the table and then talked about the ideas with, with different members of the project team.
Yes, so as your, of course, product design, and as you showed your projects from your studio in Athens, like the summer school, etc., and they are very organic, very natural based, etc. So let's say we have a brief of theatre, and then, well, Zaha did, for example, as you showed, auditorium, etc., the example of the project. It's coming up with such an organic thing. On what kind of base?
Yes. So if I take the example of the Opera Theatre House in Morocco, what you would see if I was to do the actual presentation of that the office did, it would start off with the unique features of the area. So this particular project is based on the riverside of Rabat. Rabat is a city, one of the big cities of Morocco. So it's situated next to the river there. And the team would make a lot of research about the different natural elements and formations of that city. And in fact, they discovered that there are a lot of different, small rivers and dunes that they are formed. And they were, the ones that inspired, say, this sort of curvilinear form that you would see with the actual envelope of the building. Now, keep in mind that the Opera Theatre House is a very specific building typology. It's not like it's not a housing project. It's not an office building. It needs to have a lot of different things for the auditorium to properly operate. So it would always be very bulky because of that area for the theater. So a lot of those things would define part of it. So there's also an element of being practical. But in terms of the process that the office would take, the form would be very important. And eventually everything needs to also operate. So then I would also work on making sure that a lot of the things that need to happen would be in place. Things like fire escape, not the most interesting bit, but since we're going for it, we may as well do it right. So, the form itself might be informed by different unique features of the place of the city. And also there's the identity of the office. So, as the office itself has evolved from the constructed vision to this sort of more organic, as you call it, curvilinear forms, this is a kind of language that it's using. So you would always see that sort of curves of the buildings with the projects of that office. They would usually be defined by characteristics of the nearby area. That could come through, let's say, the networks of transportation, for example. So, or that would also be informed by what other buildings might be around. The difference is that they're not straight, they're not linear buildings. So they come with a very specific set of design rules on how the curve is operated, which, I'm happy to go through, but maybe not in the in this discussion, but
No,
a lot of times,
thank you very much. I have a couple more questions. Are there any resources or books you recommend to explore this subject further? Christy asks.
Wow. So many, yes. I mean, I mentioned a lot of things. Particularly, I'm interested in sort of what you would call the system thinking that I think is very interesting to have as an architect. So I would, you could look at John Fraser's An Evolutionary Architecture. I think that's a good one. There's John Holland, Emergence from Chaos to Order. there is Mark Berry's The New Mathematics of Architecture, or Scripting Sculptures. That's also a good one. This for system thinking. Then there's what I was saying about nature and the networks around nature. So Thompson Darcy is the one I showed, the book I showed there on growth and form. I am also very much inspired by the work of a German architect called Frei Otto. He's not around anymore, but you can look up the Occupying and Connecting, it's the title of the book, or generally look him up. I think he's the one who did the the Munich stadium for the Olympics. I think this should be enough.
Yes, I believe so for now. And then another question, is there a link where we can find these workshops and projects?
Yes, my website is coming. Sorry, I do have things. I have, a lot of the times I use social media. It was mentioned again before about using social media. Yes, my website is coming up. You can follow me openly. I'm happy to have anyone connecting and talking about that because the website is not ready now. I'll be running more workshops like this. It's not going to be just in the UK, especially if you're open to traveling, and do get in touch. I do have some videos online, so if you search me online with my name and put like YouTube or Vimeo, I have some videos uploaded there. But these are only about the things that I have run as workshops that I did with different schools. Yeah, so this is the best I can say about the Link Nerd right now.
Well, I found your website of the videos on the Vimeo, so I just shared it with everyone. So hopefully they can see your projects. The rest of the projects, no idea where you can find, but it's coming up, as you said. So maybe follow Alexandros on Instagram, and he will definitely keep in touch with you. And yeah.
I'm open to have the connections, and I'm happy to have open discussions about things I talked. I'm also very much into artificial intelligence, as we saw a lot of applications previously from just the presentation, which was great. So if you really want to open up discussions on many different things around technology, please text me.
Amazing. Thank you very much, Alexandros, one more time. That was really a pleasure and a really inspirational talk and good Q&A. Thank you very much. And yes, we are about to finish. I would like to invite you for another days. For tomorrow, we have another guests and speakers. We have a day about morphology, user-focused and concept testing. So if you would like to follow us on our exhibition website and register yourself and join us tomorrow, that would be really great. We have Magda Mostafa, which is going to talk about designing for autism. We have Alicia Anselmo, which is going to talk about Bambini Holistic Children's Daycare Center. Then we have Charlie Edmonds talking about Future Architects Front. Phil Henshaw, which is going to talk about degree of permanence, and Cooking Studio. So I hope you enjoyed it and have a great evening, and see you tomorrow.